Hi, I'm Snehal Bhayani. Let me begin by welcoming you all to this presentation on our work on semi-generalized homographies for calibrated and partially calibrated cameras. We know that relative pose estimation is an important task in many applications, such as stereo pairs, structure from motion, visual localization, SLAM, etc. Typically, the relative pose is estimated between two images, but it has the disadvantage that only the direction of translation, but not its scale, can be recovered. However, if the relative pose of a pinhole camera is computed with respect to two or more images with known relative poses, then the scale becomes observable. It leads to the semi-generalized relative pose problem of estimating the pose of a pinhole with respect to a generalized camera consisting of multiple pinhole cameras. In our work, we consider the case that the scene is mostly planar, leading to the semi-generalized homography problem, which leads to a much simpler problem compared to the semi-generalized pose problem. Hence, in this paper, we studied the problem of estimating semi-generalized homography for calibrated and partially calibrated cameras. We derived linear constraints on the semi-generalized homography matrix by considering a planar scene. These constraints are then used to derive efficient minimal solvers covering all possible minimal point configurations and the number of cameras within the semi-generalized camera. Our approach allows us to estimate the relative pose as well as the scale. We also have used a special parameterization along with the technique of elimination ideals to transform a complex polynomial system into a univariate polynomial of degree 3 or 5, a linear system of one equation or a system of two equations in two variables. Let us begin with a set of 2D to 2D point matches between a pinhole camera and a generalized camera. Our objective is to estimate the rotation denoted by the matrix R and the translation denoted by the vector T, known as the semi-generalized pose, which is needed to align the pinhole camera with the generalized camera. The generalized camera system is assumed to be calibrated, whereas we have two cases for the pinhole camera where it is either calibrated or its focal length is unknown, which gives us the partially calibrated case. The 2D to 2D point matches between a pinhole and a generalized camera impose algebraic constraints on the relative pose. So let us first consider the point match Pj with Qij, where Pj is the point detected by the pinhole camera and Qij is the point detected by the pinhole Gi inside the generalized camera. Each such match gives us one polynomial equation with the unknowns being the entries of the rotation matrix R, the translation vector T, and the focal length F. Also, the vector Tgi denotes the known position of the camera Gi inside the generalized camera system. We call these equations the semi-generalized pose constraints. Hence, estimating the semi-generalized pose would require solving 6 such equations and hence 6 matches for the calibrated case. Similarly, the partially calibrated case will need 7 matches. Enliang Zheng and Chengcheng Wu proposed a set of minimal solvers for solving such constraints by considering the 4+2 and 5+1 configurations for the calibrated case and the 5+2 and 6+1 configurations for the partially calibrated case. Here, for example, 4+2, we mean that 4 matches are detected by one pinhole camera and 2 by another pinhole camera within the generalized camera system. While these solvers are useful for incremental structure from motion, the 4+2 and 5+2 configurations are too slow and hence impractical for real-world applications. In our case, the point matches come from a planar scene. So this allows us to reformulate the semi-generalized pose constraint that we saw earlier, such that each 2D to 2D point match now gives us 2 linearly independent constraints in 9 variables for calibrated case and 10 variables for the partially calibrated case. This means that we would need 5 point matches for both the cases. We must note that this reformulation has been enabled by our parameterization of the plane vector in the coordinate system of the pinhole camera P. However, this still is a complex system and it would require evaluating large impractical minimal solvers. So, in order to simplify this polynomial system, we use the semi-generalized homography matrix in order to linearize the semi-generalized pose constraint, followed by simple transformation of the plane vector. We call this the semi-generalized homography constraint. Each match then gives us 2 linear homogeneous constraints on the semi-generalized homography matrix G and the plane vector M. Thus, we have in all 10 linearly independent constraints on G and M from 5 2D to 2D point matches. The structure of the semi-generalized homography matrix G imposes additional polynomial constraints on G and M. It is quite a complex system consisting of 10 or 4 polynomials in 12 variables. Hence, employing the technique of elimination ideals and a variable transformation, the system can be simplified by combining this with the linear semi-generalized homography constraints that we saw previously. Thus, we end up with either a univariate polynomial of degree 3 or 5 or a system of polynomials in 2 variables. Such a simple polynomial system helps us to derive extremely efficient minimal solvers. So let us now summarize our approach for generating efficient minimal solvers. Starting with the semi-generalized homography constraints, we see that we have 10 equations in 12 variables. For the case of calibrated cameras, as we have an over-constraint formulation, there are 2 possibilities. One is where we use all 10 equations to have a one-variable reparameterization of G and M, which in turn leads to 5 univariate polynomials, and we choose one polynomial and then solve it using Stern sequences. The other possibility is to use only 9 equations leading to a system of polynomials in 2 variables from which we generate minimal solvers by using the Grobner basis-based automatic generator for minimal solvers. The formulation for a partially calibrated camera is well constrained, and hence we use all 10 constraints for a reparameterization to obtain just one univariate polynomial, which is then solved using Stern sequences. By evaluating these polynomials or the minimal solver, we estimate the semi-generalized homography matrix G, the camera calibration matrix K, and the plane vector M. Decomposing the homography matrix then gives us the relative pose as well as the scale. Based on the configurations of the points detected by the same camera within the generalized camera system, we cover all possibilities by defining various classes of minimal solvers. For the case of calibrated camera, we consider 3 classes. One where up to 2 points are detected by the same camera, another when 3 points are detected by the same camera, and the third class when 4 points are detected by the same camera. For the first 2 classes, we have considered both the over-constraint formulation as well as the well-constrained formulation. The case where 4 points are detected by the same camera is solved by estimating the homography matrix between the 2 cameras and then using the 5th point detected by a different camera to fix the scale. The over-constraint formulation gives us what we call the SH5 solvers, and the well-constrained formulation leads to what we call the SH4.5 solvers. Lastly, the case when all 5 points are detected by the same camera, we cannot estimate the scale. Similarly, for the case of partially calibrated cameras, we cover all possibilities. But because the system is well constrained in this case, we have only one type of solvers, the so-called SHF5 solvers. Unlike the calibrated case, here we cannot solve even if 4 points are detected by the same camera within the generalized camera system. A proof of this can be found in our paper. We have performed a comparison of solver stability using a synthetic scene setup with respect to the state-of-the-art semi-generalized pose solvers and the absolute pose solvers designed for our semi-generalized homography setup. The graphs seen here are for the error in the rotation estimates for the case of a calibrated camera. This experiment shows that our proposed solvers have comparable numerical stability in the presence of image pixel noise and close to planar scenes with respect to the state-of-the-art solvers. We also observed that for the calibrated case, the SH4.5 solvers have better stability in the presence of pixel noise as compared to the SH5 solvers. This is attributed to the fact that SH5 solvers use only 1 out of 5 constraints imposed by the form of the semi-generalized homography matrix, while the SH4.5 solvers use all. Hence, the SH4.5 solvers have better accuracy while decomposing in terms of the semi-generalized relative pose. We have evaluated the performance of our solvers for 2 real-world applications as well. The first of which is that of visual localization using the scenes from the Cambridge Landmarks database. While the scenes are generally non-planar, many contain 1 or 2 dominant planes. We depict the average median errors in pose and rotation over 4 scenes from the dataset, along with the solver runtimes. We can observe that even in the presence of generally non-planar scenes, our SH5 solver has the fastest runtime, while having accuracy comparable to that of the state-of-the-art E5+1 solver. This means that our faster solvers can be used to quickly estimate the inlier ratios for each image, which would then help in sampling image pairs for relative pose estimation using the E5+1 solver. We have also evaluated the performance of our solvers for estimating relative pose from a sequence of images using the Kitty dataset. The scenes in this dataset were captured by two front-facing cameras mounted on a moving vehicle. The camera pair is considered to be a generalized camera, and we estimate the relative pose between this camera and the left frame in the next image. Because some of the state-of-the-art solvers do not estimate the translation scale, the scale from the ground truth is used to calculate the position error. While our SH53 solver leads to the most accurate rotation estimates, the most accurate poses were obtained by combining the essential matrix obtained from E4+2 solver and the multiple homographies obtained from our SH53 solver. In this work, we have studied the semi-generalized homography problem, deriving a set of linear constraints that were used to propose a class of efficient minimal solvers. As indicated by our real-world experiments, the solvers work well even for those scenes that are not completely planar. This indicates an interesting direction for future work. Our proposed solvers can be combined with the more general solvers that work for non-planar scenes. Then we can have a smart algorithm for selecting the solver best suited for each scene in a data-dependent manner, and this would give us the best of both types of solvers. I thank you for your attention. Please visit our poster for more details or visit our GitHub page. Thank you.